Analytical Chemistry 1, Lesson 25. As our chemical mixture starts to include more and more equilibria, the equations become more complex. But it is just a bunch of algebra. The task is for you to be careful enough to see the analysis through to the end. Let's look at a diprotic acid. Malonic acid can be investigated with water autodissociation and two acid dissociation reactions. I'm using the shorthand A to represent all of the molecule except the two acidic protons. Here are the mass balance and the charge balance equations. Note how we multiplied the A2- concentration by 2 in the charge balance. Each such molecule brings two charges to the table and must be counted correctly. And here are the three equilibrium expressions. Again, if we use activity, it is in these equations where it would appear. It would not be found in the charge or mass balance equations. Let's find the pH of a 1 millimolar solution of malonic acid. 5 equations, 5 unknowns. Our strategy again is to combine these equations with each other to sequentially eliminate the unknown concentrations until you are left with an equation with just one unknown. Find the root of that equation and select the one root that makes chemical sense for the problem. Then substitute back into the original equations to sequentially find the concentration of each of the remaining species. For an acid such as this, it makes sense to choose H+ as the target species to solve for. Now is the time to be careful and methodical in your algebra. Watch the subscripts. Don't make a transcription error. Check your work along the way. Does it make sense? Do the units seem to be working out? Don't rush things, and we can solve this problem. Here again are our 5 equations. Start with a water autodissociation. Solve for hydroxide. Replace it in the charge balance equation. Remember to stop the video and make sure you are following the math when you need to. Look over the equations. Note that H2A is, like hydroxide, another term that appears once. A single substitution will eliminate it. Keep the new charge balance equation off to the side. Now step 2 is to solve the Ka1 equation for H2A and substitute it into the mass balance equation. Pause the video and consider where we are now. The mass and charge balance equations now have 3 unknown concentrations, down from 5, and there are now 3 remaining equations, the modified charge and mass balance expressions and the Ka2 equilibrium, because Ka1 and Kw have been inserted into the other equations already. Now you could proceed differently, but I'm going to next find a replacement for A2-. It appears twice in the mass and charge balance equations compared to HA- appearing 3 times, and it's sitting by itself in them, so it might be less complicated to replace it. The Ka2 equation is where it occurs, so we solve Ka2 for A2- and substitute it into the new versions of both charge and mass balance equations. The equations are looking a little messy, but at least we now have 2 equations with 2 unknowns. So what should be the next step? You'll find that denominators are always fouling us up. Try to get rid of them when you can. Looking at the 2 equations, we can see that if we multiply both sides of the charge balance equation by H+, that will get rid of those denominators. Multiplying both sides of the mass balance equation by Ka1 times H+ will clear that denominator up. First, the charge balance equation. This is an expression for HA- in terms of H+. Next, the mass balance equation. Now a reminder, keep your head about you. You can do this. Take the time to figure this out and make sure that you are following what is happening. It is not mysterious, and the algebra is just things you've done before. Just take it one step at a time and you can do this. We need to combine the 2 equations to get rid of the HA- term and end up with an equation in only H+, and a combination of a lot of all the other constants, of course. Now reorganize the equations by gathering together all terms in HA-. First, the charge balance, then the mass balance. Now we could solve for HA- by bringing the terms in parentheses over to the other side's denominator, but in looking ahead, it looks easier to substitute the charge balance into this version of the mass balance. And we have it. 1 equation with 1 unknown. We now just have to rearrange it into a polynomial in H+. First, get rid of that denominator. Multiply it over to the other side. Now hang on, we're almost there. Multiply out both sides term by term, and gather together like powers of H plus. And voila, we have our quartic polynomial. We just need to find its roots and identify the one that makes chemical sense. Again, a set of equations does exist to find the roots for quartic polynomials, but trust me, you don't want to go down that path. If you set up Solver in Excel and start with 1 times 10 to the minus 3 molar for the starting H plus concentration, it quickly produces the result 6.7906 times 10 to the minus 4 molar. And that makes sense. A little less than the formal concentration of the acid, since it will only partially dissociate. This would give a pH of 3.168. I ran this in MATLAB, which gave all 4 roots. Here they are. Now note that the other 3 roots are all negative, which makes no sense for a concentration. The other root is the same found by Solver. We can be confident that the pH of a 1 millimolar solution of malonic acid is 3.168. And yes, this is admittedly working under the approximation of having set all activity coefficients to 1. You can now go back to the equations and look for expressions to solve for the concentration of the other entities. When you do that, this is what you get. You can use this as a check on your work. Does the mass balance work out? Do the 3 malonate species sum to the formal concentration? It does. Note that the HA minus concentration is almost the same as the H plus concentration. Again, remember this. It will help us in our approximations in the future.